There's a reason Jupiter has 67 moons, and we're about to get number 68 whether we like it or not. Scientists and space agencies are on a mission to track 3I Atlas and try to figure out why it's headed for Jupiter. Here, new orbital calculations reveal something that's making scientists deeply uncomfortable. This thing is executing a precision approach to Jupiter's Hill radius, hitting a gravitational sweet spot with accuracy that shouldn't exist in nature. We're not talking about a close flyby. We're talking about spacecraft-level targeting of the perfect parking zone for long-term surveillance. Before we dive into this cosmic mystery, drop your location and local time in the comments below. Right now, as you're watching this, 3I Atlas is moving through space at 180,000 miles per hour. Someone in Tokyo is tracking a different moment of its journey than someone in New York or Sydney. Hit subscribe and turn on notifications because what we're watching may be the deployment phase of something that's been planned for longer than human civilization has existed. Now let's dim the lights and dive into this together. You know what keeps astronomers up at night? It's not an asteroid, it's not black holes, it's not even the fact that 95% of the universe is invisible to us. What really haunts them is precision where there shouldn't be any. When something from the cosmic void arrives at our doorstep, moving with the exactness of a launched satellite, that's when things get interesting. That's when things get uncomfortable. And that's exactly what's happening with 3I Atlas, an object we've been calling a comet, but which might be something else entirely. Something deliberate. Let me walk you through what has everyone so rattled. 3I Atlas entered our solar system in 2024, and at first glance it looked like your standard issue interstellar visitor. A little ice, a little rock, probably tumbling through space for millions of years before wandering into our neighbourhood by accident. Astronomers logged it, tracked it, and prepared to watch it swing around the sun and disappear back into the darkness. Business as usual. Except then someone actually ran the numbers on where this thing was going. Not just where it came from, but where it's headed. And that's when the math stopped making sense. 3I Atlas is not on a random inbound path. It's not drifting aimlessly through the solar system like some cosmic tumbleweed. The trajectory calculations show something far more unsettling. This object is moving toward a very specific destination, a gravitational sweet spot around Jupiter called the Hill radius, and it's hitting that target with a precision that shouldn't exist in nature. We're talking about spacecraft-level accuracy here. The kind of exactness you only see when something is being guided or controlled. So what exactly is the Hill radius? Think of it as Jupiter's personal gravity bubble, the region of space where Jupiter's gravitational influence dominates over the Sun's. Inside this boundary, objects feel Jupiter's pull more strongly than the Sun's, which makes it the perfect parking zone for satellites. Natural moons form here. Human-made probes aim for this zone when they want to orbit Jupiter efficiently. It's the gravitational equivalent of a harbour, a stable place where something can stay without burning through fuel or fighting against competing forces. Jupiter's Hill radius extends roughly 53 million kilometres from the planet's centre. It's enormous, a cosmic territory roughly the size of Mercury's entire orbit around the Sun. Now here's where things get weird. The calculated intercept point for 3I Atlas, 53.445 million kilometres, plus or minus 0.6 million kilometres. That's not close. That's pinpoint accurate. That's threading a needle on a galactic scale. To put this in perspective, imagine throwing a dart from New York and hitting the bullseye of a dartboard in Los Angeles, except the dartboard is moving, and you're also moving, and there's no air, and you threw the dart 10,000 years ago. That's the level of precision we're talking about. Natural comets don't do this. They can't. Let me be clear about what we mean by targeting versus close approach. Plenty of objects pass near planets. That's normal. Space is full of rocks and ice balls wandering around on chaotic paths. Sometimes they get close to Jupiter or Saturn purely by coincidence. But there's a massive difference between passing near something and hitting a specific gravitational boundary within a margin of error measured in thousands of kilometres. The latter requires either impossible luck or active guidance. And 3I Atlas isn't just getting close to Jupiter's Hill radius. It's hitting the boundary with surgical precision. The kind of accuracy that mission planners at NASA spend years calculating for actual spacecraft. The official designation from NASA still classifies 3I Atlas as a comet. That's the bureaucratic label in the database. But a growing number of independent astronomers, including Avi Loeb's team at Harvard, are now arguing publicly that the observational data doesn't fit a natural comet at all. Instead, they say the trajectory matches what you'd expect from an insertion maneuver, a controlled approach designed to place an object into a specific orbital zone. This isn't fringe stuff anymore. These are credible scientists with access to the same data NASA has, and they're looking at the numbers and reaching a very different conclusion. Here's what makes the situation even stranger. 3I Atlas approached perihelion, its closest point to the Sun, back in early 2025. Comets typically behave erratically after perihelion because the solar heat causes volatile ices to sublimate violently, creating jets of gas that push the comet around unpredictably. You'd expect the trajectory to loosen up to become messier and harder to predict. Instead, the opposite happened. The approach vector tightened. The path toward Jupiter's Hill radius became more refined, more exact, as if someone had made a course correction after the Sun encounter. That's not how sublimating ice behaves. That's how thrusters behave. And then there's the Earth problem. 3I Atlas passed relatively close to Earth on its way to Jupiter, close enough that if this were an alien probe interested in humanity, you'd expect some kind of response, a change in orientation, maybe a shift in velocity, some kind of thermal signature indicating observation equipment activating. But nothing happened. No braking, no orientation change, no thermal anomalies. The object completely ignored us. It flew past Earth like we weren't even there, like a car on the highway passing an exit without slowing down. That indifference is more disturbing than hostility would be, because it suggests we're not the destination. We're just scenery on the way to somewhere more important. But here's the detail that really gets under your skin. During the period when 3I Atlas was hidden behind the Sun from Earth's perspective, something happened. The object accelerated slightly. Not a lot, just enough to be measurable, but enough to adjust the trajectory in precisely the way needed to refine the approach to Jupiter's Hill radius. This acceleration occurred during solar conjunction, a window of time when solar glare prevents telescopes from tracking objects accurately. Convenient timing, if you think about it. Almost like someone knew when they wouldn't be watched closely. If 3I Atlas is a vehicle, if it's a carrier craft of some kind, then its flyby of Earth makes perfect sense. We were never the target. We were never part of the mission plan. The real event, the actual objective, happens at Jupiter. And that possibility, that we might be witnessing the arrival of something intentional, something with a specific goal that has nothing to do with us, changes everything we thought we understood about our place in the solar system. Because if something out there is building infrastructure around Jupiter, we need to know what that infrastructure is for. And more importantly, we need to understand why they're building it right next door. Now let's talk about what happened during those critical hours when we couldn't see 3I Atlas. There's a specific kind of paranoia that astronomers rarely talk about publicly, but it's there, lurking beneath the surface of every conversation about interstellar objects. It's the fear of the blind spot, the terror that something could happen in the one place we can't see, during the one window when our instruments go dark and we'd never know until it was too late. For 3I Atlas, that blind spot was solar conjunction, and what happened during those hours has become the most hotly debated mystery in modern astronomy. Solar conjunction is a predictable event. It happens when Earth, the Sun, and a target object align, placing the Sun directly between us and whatever we're trying to observe. During this period, solar glare overwhelms our telescopes. Radio signals get swamped by the Sun's electromagnetic noise. Optical observations become impossible. We go blind for anywhere from a few days to several weeks depending on how close the alignment is. For 3I Atlas, the blackout window lasted between 40 and 60 hours, a relatively short conjunction, but long enough that precise tracking became impossible. When the object emerged from behind the Sun's glare, astronomers immediately noticed something had changed. The change was subtle but unmistakable. 3I Atlas had experienced what scientists call a non-gravitational acceleration event. In plain English, something had pushed the object in a way that gravity alone couldn't explain. The velocity had increased slightly, and more importantly, the direction had shifted in precisely the manner needed to refine the approach to Jupiter's Hill radius. This is where the scientific community splits into two camps, each offering radically different explanations for what they're seeing in the data. The conventional explanation goes like this. Comets are dirty snowballs. mixtures of ice and rock left over from the solar system's formation. When they get close to the Sun, the ice heats up and sublimates, turning directly from solid to gas without passing through a liquid phase. This outgassing creates jets of vapor that can push the comet around, producing measurable accelerations that aren't caused by gravity. It's a well-documented phenomenon. We've seen it happen with dozens of comets over the years. So when 3I Atlas showed a non-gravitational acceleration after perihelion, the natural assumption was that solar heating had triggered outgassing, and the resulting jets had nudged the object onto a slightly different path. Case closed. Mystery solved. Nothing to see here. But here's where the conventional explanation starts to break down under scrutiny. Cometary outgassing is chaotic by nature. When ice sublimates on an irregularly shaped rotating body, it creates jets pointing in random directions. These jets appear and disappear as different parts of the comet rotate into and out of sunlight. The result is usually a tumbling, erratic motion that's extremely difficult to predict. Comets don't fly straight after perihelion. They wobble, they spin, they change direction in ways that require constant recalculation. Yet 3I Atlas displays an unusually symmetrical coma, the cloud of gas and dust surrounding the nucleus. There are no detectable jets, no rotating outgassing sources, none of the typical signs of asymmetric sublimation. The object looks remarkably stable, almost artificially so. More troubling is the direction of the acceleration. When you map the velocity change vector, when you calculate exactly which way the push occurred, it points in the precise direction needed to tighten the approach to Jupiter's Hill radius. Not approximately, not close enough, exactly. It's as if someone calculated the optimal correction burn and executed it with textbook precision. Natural outgassing doesn't work that way. Gas jets from sublimating ice don't care about orbital mechanics. They push randomly, and the resulting trajectory changes are messy and unpredictable. This was clean. This was targeted. Some astronomers have pointed out that certain comets do exhibit asymmetric heating patterns that can create surprisingly consistent thrust over short periods. If the ice distribution inside the nucleus is non-uniform, if there's a concentration of volatiles on one side of the object, then heating from the Sun could theoretically produce a more directional acceleration. It's possible, though unlikely, that 3I Atlas just happened to have exactly the right internal structure to create exactly the right push in exactly the right direction at exactly the right time. Possible. But when you string together that many coincidences, you start to wonder if you're looking at bad luck or deliberate design. Then there's the timing issue. The acceleration occurred during the telemetry blackout, the 40 to 60 hour window when precise tracking wasn't possible. Not before conjunction when we could have watched it happen in real time. Not after the object was fully clear of solar glare when we could have measured every detail. Right in the middle of the blind spot when verification was impossible. Skeptics will correctly point out that this timing makes perfect sense for a natural explanation too. Perihelion is when comets are most active, and perihelion coincides with conjunction, because that's just how orbital geometry works. The Sun is in the way because the comet is closest to the Sun. It's not suspicious, it's just physics. But if you were designing a probe that needed to make a course correction, if you wanted to adjust your trajectory without drawing attention, you'd do it here too. You'd wait for perihelion because the solar energy is strongest, giving you maximum power for any onboard systems. You'd wait for conjunction because Earth's telescopes can't track you precisely. And if your propulsion system happened to produce exhaust that looked a lot like sublimating ice, well, that's just good camouflage. Solar heating provides both energy and cover. It's the perfect moment for a burn, natural or otherwise. After conjunction, after the acceleration, 3I Atlas entered what some researchers are calling the corridor. This is a specific volume of space, a narrow pathway defined by gravitational forces and orbital mechanics that leads directly to the Hill radius intercept. Once you're in the corridor, once you're on this particular trajectory with this particular velocity, you're locked in. The path is set, and 3I Atlas is deep in the corridor now, moving inexorably toward its rendezvous with Jupiter's gravitational boundary. The question that nobody can answer definitively is whether the object entered the corridor by chance or by choice. Did random outgassing happen to push it onto the one trajectory out of billions that leads precisely to the Hill radius? Or did something make a deliberate adjustment during the one window when we couldn't watch closely? The data can support both interpretations, which is why this debate has become so contentious. Scientists are looking at the same numbers and reaching opposite conclusions because the margin between natural and artificial behaviour is razor thin. If this was a course correction, if 3i Atlas used perihelion as a cover for a controlled burn, then we're dealing with something that understands orbital mechanics at an advanced level. Something that knows how to use solar radiation for power or propulsion. Something that planned this manoeuvre long before entering our solar system, calculating the exact moment and magnitude of thrust needed to hit the target. And something that may have deliberately chosen a method of propulsion that mimics natural processes, making it almost impossible for observers to distinguish between accident and intent. That level of sophistication is frankly terrifying because it suggests we're not just being visited, we're being strategically approached by something that doesn't want to be identified until it's ready. But let's talk about what didn't happen, because sometimes absence is more revealing than presence. Let's examine the Earth flyby more closely, because the complete lack of interest 3i Atlas showed in our planet might be the most unsettling aspect of this entire mystery. Humanity has spent the better part of a century imagining first contact. We've written thousands of books, made hundreds of films, and developed countless protocols for how we'd respond if something intelligent arrived from the stars. Most of these scenarios involve some form of interaction: hostile invasion, peaceful greeting, scientific exchange, cultural misunderstanding. Whatever the specifics, we always assume they'd notice us. We assume we'd matter. 3i Atlas is forcing us to confront a far more unsettling possibility. What if we don't matter? What if something arrived from another star system, passed right by Earth, and didn't even slow down to look? The psychological impact of this indifference is difficult to overstate. We're conditioned to think of ourselves as important, as the centre of the story. When we look at the cosmos, we imagine civilizations out there wondering about us the same way we wonder about them. We picture alien telescopes pointed at Earth, scientists on distant worlds debating whether our radio signals indicate intelligence or just natural phenomena. We envision scenarios where contact happens because they seek us out or we seek them out. But either way, there's mutual interest. 3i Atlas challenges that entire framework. If it's artificial, if it's a probe or vessel of some kind, then its complete disinterest in Earth tells us something profound and deeply uncomfortable about our cosmic significance. Let me walk through what didn't happen during the Earth flyby. 3i Atlas passed within a range where any probe equipped with even basic sensors could have gathered enormous amounts of data about our planet. Atmospheric composition, electromagnetic emissions, thermal signatures, all the hallmarks of a technological civilization broadcasting its presence across multiple spectrums. This was an opportunity for reconnaissance, for observation, for at least a cursory scan of what's happening on this blue marble in the habitable zone, and 3i Atlas did absolutely nothing. No maneuver adjustments, no orientation changes that might indicate cameras or sensors swiveling toward Earth, no thermal variations suggesting equipment activating, no unusual radio reflections, no albedo changes, nothing. From an engineering standpoint, ignoring Earth makes sense only if Earth wasn't part of the mission parameters. If you're driving from New York to Los Angeles, you don't stop in every small town along the way unless you have a specific reason to. You might glance out the window as you pass through, but you don't exit the highway for a closer look unless something catches your interest. 3i Atlas drove right past us without taking the exit, which tells us that whatever its destination and purpose might be, we're not it. We're just one more G-type star with some rocky planets. Nothing worth the fuel expenditure for a detour. But here's where it gets interesting from a strategic perspective. If you're an advanced civilization sending probes to other star systems, Jupiter is exactly where you'd want to set up shop. Not Earth, not Mars, Jupiter. And there are very good reasons for this choice that have nothing to do with biology or habitability, and everything to do with energy and positioning. Jupiter's magnetosphere is the largest and most powerful in the solar system, a massive region of charged particles and magnetic fields that dwarfs anything Earth can produce. For any civilization that knows how to tap electromagnetic energy, Jupiter is a cosmic power plant. Free energy on a scale that makes even Dyson sphere concepts look quaint. You could run entire fleets of autonomous probes indefinitely just by harvesting what Jupiter's magnetosphere generates naturally. Then there's orbital stability. The Hill radius isn't just a gravitational boundary, it's a parking zone where objects can remain in relatively stable orbits, without constant course corrections. You could place a satellite or probe in this region, and it would stay there for centuries with minimal station-keeping requirements. No fuel burned, no complex maneuvers, just letting Jupiter's gravity do the work of keeping your hardware in position. For a long-term observation mission, for anything designed to monitor a star system over extended timescales, this is ideal. Real estate. And the view from Jupiter is spectacular, at least from a surveillance perspective. You're far enough out that you can see the entire inner solar system spread out before you. Earth, Mars, Venus, Mercury, all visible, all trackable. Radio emissions from Earth would wash over your position constantly. You'd have a front row seat to everything happening in the warm inner orbits, where rocky planets and complex chemistry create the conditions for life. Meanwhile, you're sitting in a radiation-soaked magnetic hellscape where nothing biological could survive, which means any organic civilization like ours isn't going to come poking around your equipment anytime soon. It's the perfect observation post. Close enough to see everything, but far enough to remain undisturbed. This strategic reasoning points to a conclusion that many people find more frightening than outright hostility. 3i Atlas might not be here for us at all. We might be incidental, background noise in a mission focused on long-term infrastructure deployment. Think about it from their perspective, whoever they are. You send a probe to a star system not to make contact with whatever primitive civilizations might be stumbling around on rocky planets, but to establish a permanent monitoring presence. You want data, you want a communications relay, you want a base of operations that can function autonomously for thousands of years, collecting information and transmitting it back home. Earth is just one of many objects in the system worth monitoring. No more special than the asteroid belt or Saturn's moons. The human fear fantasy has always been invasion. We imagine fleets of ships arriving to strip mine our resources, or enslave our population, or wipe us out as competitors. These scenarios assume we're important enough to threaten, valuable enough to exploit. The dark reality suggested by 3i Atlas is far more existentially troubling. We might not be strategically important at all. Our planet, our civilization, our entire existence might be nothing more than data points in a survey mission. Interesting enough to log, but not worth interacting with directly. We're the locals, and they're not here to conquer us or trade with us or even talk to us. They're here to set up infrastructure that serves purposes we can't even guess at. NASA and ESA maintain that 3i Atlas is a natural interstellar comet with no maneuverable capability. They point to the lack of radio emissions, the absence of any clear artificial signatures, the consistency of its behavior with known cometary physics. These are all valid points. But when you step back and look at the pattern, the precision of the trajectory combined with the complete disinterest in Earth, it paints a picture that's hard to dismiss. This doesn't look like random chance. This looks like planning. This looks like execution of a mission we're not privy to. Historians might find parallels in Earth's own colonial past, though. The comparison is imperfect. When European powers explored the Americas, they often established forts and trading posts in strategic locations, places with good harbours or access to rivers or defensive advantages. The indigenous populations nearby were sometimes engaged with, sometimes ignored, depending on whether they were seen as useful or threatening or irrelevant. 3i Atlas might represent that same calculated assessment, applied on an interstellar scale. Jupiter is strategically valuable. Earth is not yet relevant enough to engage with directly, and that realization, that we might be the indigenous population watching ships sail past to a more important port, is a humbling and terrifying prospect. Because it means contact, if it ever comes, will happen on their terms and their timeline, when and if they decide we're worth the effort of saying hello. Now let me explain something that doesn't get discussed much in public forums, probably because it sounds too much like science fiction even though it's based on perfectly reasonable physics. There's a concept in astrobiology called Sentinel theory. The idea is that advanced civilizations don't send themselves to other star systems. They send machines, small, durable, autonomous probes that can survive the journey, arrive at the destination, and then do something we rarely consider in our contact fantasies. They multiply, they disperse, they build networks. This is the core of Sentinel theory. And 3i Atlas might be giving us a front row seat to exactly how such a deployment operation works. Let me explain what Sentinel theory actually proposes, because the details matter. The theory suggests that interstellar exploration isn't conducted by massive crewed vessels, or even single large probes. Instead, a carrier craft arrives at the target star system carrying dozens or even hundreds of smaller autonomous units. These units are designed for long-term monitoring and data collection. The carrier approaches a gravitationally stable region, something like Jupiter's Hill radius, and then performs a dispersion event. The smaller probes detach, break into different orbits using minimal propulsion, and position themselves at strategic points throughout the system. Some might head for Lagrange points, others might settle into orbits around major planets or moons, a few might even venture into the inner system to observe rocky planets more closely. The beauty of this approach from an engineering standpoint is efficiency. You don't waste energy and resources sending individual probes to every star system. You send one carrier that can deploy a complete observation network upon arrival. Once the deployment is complete, the carrier either stays in system as a communications hub or continues on to the next target, leaving the network to operate autonomously. Over time, over thousands or millions of years, this strategy could fill the galaxy with Sentinel networks, each one quietly monitoring its assigned star system and transmitting data back to whoever built them. If any of these systems develop technological civilizations, the Sentinels are already in place to observe, record, and report. Jupiter's Hill radius is nearly perfect for this kind of operation, and understanding why requires a bit of orbital mechanics. The Hill radius defines the region where Jupiter's gravity dominates, but within that region are even more refined zones of stability called Lagrange points. These are specific locations where the gravitational forces of Jupiter and the Sun balance in ways that allow objects to maintain fixed positions relative to both bodies. The L1 and L2 points are particularly interesting because they sit along the line connecting Jupiter and the Sun, creating natural parking spots where a probe could hover indefinitely, with minimal energy expenditure. L1 sits between Jupiter and the Sun, about 50 million kilometers from Jupiter's center. An object at L1 can observe both the inner solar system and Jupiter itself without ever leaving that position. It's a surveillance platform that requires almost no fuel to maintain. L2 sits on the far side of Jupiter, roughly the same distance out but in the opposite direction. An object at L2 is perpetually in Jupiter's shadow from the Sun's perspective, making it nearly invisible to Earth-based telescopes. It's the perfect hiding spot, a dark zone where you could park an entire fleet of probes and nobody would notice unless they went looking specifically. The Hill radius and Lagrange points together create a three-dimensional lattice of stable positions where autonomous probes could position themselves for centuries or longer. No complex station-keeping maneuvers, no fuel burned fighting against gravitational perturbations, just pure celestial mechanics doing the work of maintaining position. For a civilization thinking on timescales of thousands of years, this is how you build lasting infrastructure in a foreign star system. You use the gravity wells and orbital resonances that are already there, turning the system's physics into your anchor points. Jupiter itself offers additional advantages that make it ideal for long-term autonomous operations. The magnetosphere is enormous, extending millions of kilometers in all directions and carrying enough energy to power entire cities. Any probe equipped with electromagnetic harvesting technology could draw continuous power from the charged particle flux, eliminating the need for nuclear reactors or solar panels. You could run sophisticated sensor arrays, communication systems, and computation hardware indefinitely, without worrying about batteries dying or fuel running out. The radiation environment, while lethal to biological organisms, is actually protective for certain types of electronics. High-energy particles can damage semiconductors, yes, but they also create a natural barrier against detection. Radio signals get scattered and absorbed by the plasma. In the magnetosphere, optical observations are difficult because the background glow from auroras and particle interactions creates noise. If you wanted to hide electronic signatures from primitive civilizations in the inner system, Jupiter's radiation belts are nature's perfect jamming system. So what would deployment actually look like from an observational standpoint? This is where things get speculative but grounded in physics we understand. Imagine 3i Atlas approaching the Hill radius boundary over the next few months. As it crosses into Jupiter's gravitational domain, instruments on Earth might detect what appears to be a fragmentation event. Not an explosion, nothing violent, just the parent object coming apart into multiple smaller pieces. This happens with natural comets all the time, so initially, nobody would think twice about it. Ice and rock separating due to tidal forces or thermal stress. Perfectly normal. But then the fragments don't behave like comet debris. Instead of dispersing chaotically, they break cleanly. They slow down in coordinated ways. They begin moving toward different destinations, some heading for L1, others toward L2, a few perhaps diving deeper into the Jovian system toward Io or Europa. The individual objects are small, maybe a few meters across, with low albedo surfaces that make them nearly impossible to track optically. Within weeks, they've scattered across the Hill radius region, each one settling into a stable position where it can monitor the inner solar system indefinitely. From Earth, we'd see a comet that fragmented near Jupiter. Nothing unusual about that. What we wouldn't see is the network being established right under our noses. Dozens of autonomous probes taking up residence in the solar system's gravitational furniture. They'd be too small to resolve individually, too faint to detect unless you knew exactly where to look, and operating in a radiation environment that makes electronic reconnaissance nearly impossible. By the time anyone realized something strange had happened, the deployment would be complete and the network operational. Some researchers have pushed this theory even further into speculative territory. They argue that 3I Atlas might not be the first carrier to arrive. Oumuamua, the first confirmed interstellar object detected in 2017, exhibited bizarre acceleration patterns that some interpreted as a light sail or outgassing from an unusual composition. But what if Oumuamua was a scout, a preliminary probe sent to assess the solar system before the main mission arrived? What if 3I Atlas is actually a resupply vessel, or a node delivery craft for a network that's already been here for years, hidden in plain sight among Jupiter's dozens of known irregular moons? This is unverified. Let me be clear. There's no direct evidence that previous interstellar objects were artificial, or that any kind of probe network currently exists around Jupiter. But the pattern fits. Theoretical models proposed by scientists studying how advanced civilizations might explore the galaxy. You don't visit each system once and leave. You establish permanent presence. You create infrastructure that can observe and report over geological timescales. And you do it quietly, using the natural environment to hide your activities from whatever primitive civilizations might be emerging on rocky planets in the habitable zone. If Sentinel theory is correct, if 3I Atlas is here to deploy a monitoring network, then we're witnessing something unprecedented in human history. We're watching in real time as our solar system gets claimed by an intelligence that didn't bother to ask permission or announce its intentions. They're moving in next door, setting up permanent surveillance, and we have no way to stop it and no clear method even to confirm it's happening. The probes would be small, silent, and strategically positioned in places we rarely look. By the time we develop the technology to search for them properly, they'll have been watching us for decades, collecting every radio transmission, tracking every satellite launch, recording every step of our stumbling progress toward becoming a spacefaring civilization ourselves. And the truly terrifying part, we might never know they're there until they decide it's time to let us know. But here's what we do know right now, what the data is showing us in real time as 3I Atlas continues its journey toward Jupiter. The trajectory hasn't deviated. The precision hasn't degraded. Whatever happened during solar conjunction, whatever adjustment was made or natural process occurred, it locked this object onto a path that leads directly to the one region of space where long-term monitoring makes the most sense. And as March approaches, as we get closer to the moment when 3I Atlas crosses into Jupiter's Hill radius, the tension in the astronomical community is building. Because everyone knows we're about to see something. The question is whether we'll recognize it for what it is when it happens. Will we see a comet fragmenting naturally under tidal stress? Or will we see something else? Something that moves with purpose, that breaks apart in coordinated ways, that deploys components into orbits that make no sense for random debris but perfect sense for a surveillance network. The telescopes are ready. The observation campaigns are planned. Hubble, James Webb, every major ground-based observatory will be watching when 3I Atlas reaches Jupiter. We're going to get data. Lots of data. The question is whether that data will answer our questions or just deepen the mystery. Because that's how it always works with these interstellar visitors. Every observation raises new questions. Every measurement reveals new anomalies. And we're left trying to build explanations from fragments of information, knowing that whatever the truth is, it's probably stranger than anything we've imagined so far. That's where the story stands right now. An object from beyond our solar system, moving with impossible precision toward a gravitational sweet spot around Jupiter, showing behavior that straddles the line between natural and artificial so perfectly that we can't definitively prove either case. And in a few months, maybe weeks, we're going to watch what happens when it gets there. We're going to see whether 3I Atlas is just another weird comet in a universe full of weird things, or whether it's something that will force us to rewrite everything we thought we knew about our place in the cosmos, about whether we're alone, about whether anyone out there is watching, about whether the galaxy has already been mapped and catalogued and monitored by intelligences we've never noticed, because we weren't looking in the right places or thinking on the right timescales. The mathematics are undeniable, the precision is real, the trajectory is set, and whatever happens next at Jupiter, whatever we see or don't see when 3I Atlas crosses that boundary, it's going to tell us something profound about the universe we inhabit, and our readiness to understand what's really happening in the darkness between the stars. But before we can understand what might happen at Jupiter, we need to understand what the scientific community is actually debating behind closed doors, because the public narrative and the private arguments are two very different things. Scientific consensus is a fragile thing, especially when it comes to objects that don't behave the way textbooks say they should. 3I Atlas has become a lightning rod for debate within the astronomy community, splitting researchers into camps that view the same data through entirely different interpretive frameworks. The public sees a unified scientific front, press releases from NASA and ESA describing a fascinating interstellar comet. Behind the scenes, in academic journals and conference presentations and private correspondence, there's a war being fought over what this object actually is and what its trajectory really means. The central question is deceptively simple. Can natural outgassing explain the observed trajectory, or does the precision of the approach to Jupiter's hill radius require active guidance? This isn't a philosophical debate, it's a mathematical one, and math doesn't care about what we want to believe. The problem is that small uncertainties in the initial observations get magnified enormously when you try to project a trajectory backward across interstellar distances or forward to a specific target. An error of 0.001 degrees in the angle becomes millions of kilometers of uncertainty by the time you reach Jupiter. So when skeptics argue about the hill radius intercept, they're not denying the numbers, they're questioning whether the numbers are precise enough to distinguish between coincidence and intent. Let me break down the arguments against the natural explanation because they're more sophisticated than simple conspiracy thinking. First, there's the issue of trajectory refinement. Cometary jets produce thrust. That's well-established physics. But the thrust is directionally random unless you have a very specific internal structure that creates asymmetric outgassing. The ice has to be concentrated on one side of the nucleus. The rotation has to be aligned so that the sublimating surface faces the right direction. And the timing of the outgassing has to coincide perfectly with the moment when a course correction is needed. String all those requirements together and you're asking for a very specific set of coincidences. Possible? Yes. Likely? That's where opinions diverge. Second, there's the coma symmetry problem. Most active comets display irregular, patchy comas with visible jets streaming from specific regions on the nucleus. The jets appear and disappear as the comet rotates, creating a time-variable appearance that astronomers can map to understand the object's shape and spin. 3I Atlas doesn't show this behaviour. Its coma is unusually uniform, almost eerily smooth, as if the outgassing is happening evenly across the entire surface or not happening at all. Some researchers argue this could result from a very slow rotation period or a nearly spherical shape, both of which are rare but possible. Others point out that a smooth coma is exactly what you'd expect from an artificial object, with no outgassing at all, just reflected sunlight and maybe some surface ablation from micrometeoroids. Third, there's the fragmentation rate issue. Natural comets falling apart near the Sun typically show dramatic breakup events, with large fragments separating and distinct debris trails forming over days or weeks. 3I Atlas has been remarkably intact throughout its journey. Minor debris has been detected, yes, but nothing like the catastrophic fragmentation you'd expect from a loosely bound pile of ice and rock undergoing extreme thermal stress. It's holding together better than most comets do, which is strange for an object supposedly undergoing violent outgassing strong enough to change its trajectory. Now let's look at the arguments in favour of the natural explanation, because they're equally valid and grounded in real physics. Comets are weird. We've studied dozens of them up close, and every single one surprises us with unexpected behaviour. Some have multiple active regions that turn on and off seemingly at random. Others show delayed outbursts days or weeks after perihelion as heat penetrates into the interior. a few have exhibited sustained thrust in specific directions due to nothing more exotic than asymmetric ice distribution and solar heating. Comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft studied extensively, showed complex outgassing patterns that looked almost artificial in their regularity, but were ultimately traced to the comet's weird duck-shaped structure and how different regions heated up as it rotated. The math of orbital fitting is genuinely tricky when you have limited observations spread across months, when you're trying to account for gravitational perturbations from multiple planets, when you're dealing with non-gravitational forces that might or might not be present. The resulting trajectory calculations have error bars. Those error bars can hide a lot of uncertainty. Maybe the Hill radius intercept isn't as precise as it appears. Maybe we're seeing an artifact of how the data was processed, which orbital models were used, which observations were weighted most heavily in the fit. Garbage in, garbage out applies even in astronomy. Bad data produces bad conclusions, and we won't know if the data was actually good enough until we see what happens when 3i Atlas actually reaches Jupiter. There are also internal technical debates that rarely get discussed outside specialist circles. For example, different models of ice behavior produce different predictions for how comets should move. Crystalline ice sublimates differently than amorphous ice. Water ice behaves differently from carbon dioxide ice or methane ice. If 3i Atlas has an unusual composition, something we haven't seen before because it formed in a different stellar system with different chemistry, then all our models for how it should behave might be wrong. We could be looking at perfectly natural physics that just doesn't match what we're used to seeing in solar system comets. Then there are the whispers, the fringe claims that circulate in online forums and occasionally leak into more respectable venues. Some people insist that early tracking data was smoothed or filtered to remove anomalies, that certain observations didn't fit the comet narrative and were quietly excluded from the official orbital solutions. Others claim that the Hill radius match was noticed much earlier than publicly acknowledged, but kept quiet to avoid triggering public panic or conspiracy theories. A few voices suggest that JPL quietly revised its orbital calculations after community pushback, tweaking the numbers to make the trajectory look more natural. These claims are unverified and mostly unprovable. Institutional astronomy operates with enough transparency that large-scale data manipulation would be difficult to hide, but the fact that these whispers exist tells you how divisive this object has become. What's not in dispute is the observational mystery at the core of this whole debate. 3i Atlas has a persistent forward-facing halo, a slight brightening in the direction of travel that doesn't match typical comet dust distribution. It's fragmenting more slowly than thermal models predict. No major jets have been detected in any spectroscopic observations, which is weird for something supposedly active enough to change its own orbit. The data is real. The measurements are solid. The mystery is in figuring out what story the data is telling us. Are we looking at a natural comet with an unusual composition and structure that happens to be approaching Jupiter with improbable precision? Or are we looking at something artificial that's mimicking natural processes well enough to maintain plausible deniability? The scientific method demands that we default to natural explanations until evidence conclusively rules them out. But as the trajectory gets refined with each new observation, as the approach to the Hill radius gets confirmed again and again, the uncomfortable questions get harder to dismiss, because at some point coincidence stops being a satisfying explanation, and you have to consider alternatives that challenge everything we thought we knew about our place in the galaxy. Now let's talk about something that should terrify you, or at least make you deeply uncomfortable. 3i Atlas doesn't exist in isolation. It's the third confirmed interstellar object we've detected passing through our solar system, and when you line up all three and examine their properties side by side, a pattern starts to emerge. Or maybe it doesn't. Maybe we're just pattern-seeking primates staring at random noise and inventing narratives. But the data points are there, undeniable, and they're weird enough that even conservative astronomers are starting to ask uncomfortable questions about what's really flying past our cosmic doorstep. Let's start with Oumuamua because that's where this whole interstellar object obsession began. Detected in October 2017, Oumuamua was like nothing we'd ever seen before. Its trajectory confirmed it came from outside the solar system, which was exciting enough on its own. But then the observations started rolling in, and nothing made sense. The object was elongated, maybe 10 times longer than it was wide, with a highly reflective surface. It tumbled through space in a complex rotation pattern, and most bizarrely, it accelerated away from the Sun in a way that couldn't be explained by gravity alone. Something was pushing it, but there was no visible coma, no tail, no signs of the outgassing that should accompany cometary acceleration. Avilo proposed that Oumuamua might be a light sail, a thin artificial structure pushed by solar radiation pressure. This idea was met with enormous skepticism, and rightly so. Extraordinary claims require extraordinary evidence, and the evidence for artificial origin was circumstantial at best. But the natural explanations had problems too. If Oumuamua was a comet, why no coma? If it was just a weird rock, what caused the acceleration? Hypotheses involving hydrogen icebergs or nitrogen ice from Pluto-like worlds got proposed and debated, each with its own set of assumptions and difficulties. 5 years later, we still don't have consensus on what Oumuamua actually was. Then came Tuohy-Borisov in 2019, and this one looked reassuringly normal. It had a proper coma. It showed outgassing consistent with water ice and carbon monoxide. Spectroscopic analysis revealed a composition similar to solar system comets. Tuohy-Borisov let everyone relax a little. Proof that most interstellar objects are probably just interstellar comets. Nothing exotic, nothing artificial, just chunks of ice and rock ejected from other stellar systems during planet formation, wandering the galaxy until they happened to pass through ours. Crisis averted, normal science restored. And now we have 3I Atlas, which somehow manages to be more unsettling than Oumuamua despite looking more like a conventional comet. It has a coma. It shows signs of activity. But the trajectory is too precise, the acceleration too well timed, the target too specific. It's like someone learned from Oumuamua's mistakes, figured out that obvious anomalies attract too much attention, and designed the next probe to be just comet-like enough to avoid immediate detection while still accomplishing its mission objectives. That's paranoid thinking, I'll admit. But when you're dealing with objects that might be the first evidence of extraterrestrial technology, a little paranoia feels justified. The scientific frameworks for understanding these objects are evolving rapidly. Light sail hypotheses aren't just about Oumuamua anymore. Researchers are exploring how thin film materials, possibly just micrometers thick, could be pushed by solar radiation across interstellar distances. You don't need engines or fuel, just a large surface area and patience. Launch 1,000 light sails toward nearby star systems and wait 1,000,000 years. Some will arrive, some will collide with debris, some will get pulled into stars, but a few will make it through, and those few can deploy their payloads and start observing. Hollow body hypotheses suggest that interstellar probes might be designed as shells rather than solid objects, maximizing surface area while minimizing mass. This makes them easier to accelerate and harder to detect because they don't reflect light the way solid bodies do. Some researchers are even exploring fractal geometries, structures that repeat at multiple scales to create enormous effective surface areas within compact volumes. These are all speculative ideas, but they're based on physics we understand. If we wanted to send probes to other star systems with current or near-future technology, these are the designs we'd consider. Then there's the truly speculative but mathematically interesting idea of dark visitors. Not every object passing through the solar system gets detected. We find the ones that are bright enough, large enough, or close enough to see. But small, dark objects moving through the outer solar system could slip past unnoticed, unless they happen to pass in front of a star or reflect sunlight at just the right angle. How many interstellar objects have we missed? How many are passing through right now that we simply can't see? The answer is probably a lot, and that statistical reality creates space for all kinds of unsettling possibilities. Avi Loeb and others have proposed that we might be surrounded by a galactic communication network we don't recognize. Not radio signals, those we detect, but something more subtle. Gravitational wave modulations, neutrino beam patterns, quantum entanglement channels, whatever the physics of advanced communication turns out to be. These signals might be washing over Earth constantly, and we'd have no idea because we're not listening in the right way. It's like trying to detect Wi-Fi with a transistor radio. The signals are there, but you need the right receiver to pick them up. Autonomous probe networks make even more sense when you consider the timescales involved in galactic exploration. Light takes years to cross interstellar distances. Even at relativistic speeds, travelling between stars requires decades or centuries. No civilization is going to maintain real-time control over probes operating hundreds of light-years away. Instead, you build autonomous systems that can make decisions, adapt to local conditions, and carry out long-term missions without constant supervision. You send them to gravitationally stable regions around stars and gas giants, where they can observe for thousands of years, collecting data and transmitting summaries back home whenever a faster probe swings by to act as a courier. Jupiter keeps coming back as the obvious choice for this kind of infrastructure. If you were cataloguing stellar systems across the galaxy, looking for ones that might develop technological civilizations, you'd want probes in places that offer good vantage points and long-term stability. Gas giants with strong magnetospheres fit that requirement perfectly. They're easy to find, easy to reach, and they provide natural resources for probe operations. Jupiter isn't special in this framework. It's just one of millions of similar locations scattered throughout the Milky Way, each one potentially hosting its own Sentinel network. Some models propose that interstellar probes follow power gradients, seeking out high-energy environments where they can recharge and maintain operations. Stars, obviously, but also magnetospheres, accretion disks, planetary radiation belts, anywhere electromagnetic fields and charged particles create harvestable energy. If this hypothesis is correct, then Jupiter isn't just a convenient parking spot. It's a refueling station, a place where probes naturally congregate because the physics of energy extraction favours these locations. There's a historical pattern worth noting here. Throughout human history, surveillance and reconnaissance have always involved finding high ground. Mountaintops, satellites, Lagrange points. We put our observation platforms where they can see the most territory with the least effort. If aliens think the same way, if convergent evolution applies to military and intelligence strategy, as much as it does to biology, then Jupiter's hill radius is the cosmic equivalent of the high ground. You can see everything from there, and anything happening on Earth is visible in real time, or at least in the 12 to 40-minute light lag depending on orbital positions. Imagine a galaxy filled with these networks. Millions of Sentinel systems deployed over billions of years, each one quietly monitoring its assigned star. Some watch systems with primitive life. Others observe worlds undergoing technological development. A few might be tracking civilizations far more advanced than ours. The probes don't interfere, they just record and transmit. And somewhere far away, something is receiving all that data, building a comprehensive map of galactic development, tracking which systems show promise and which ones collapse before reaching the stars. Maybe the probes activate under certain conditions. Maybe they're designed to remain dormant until a civilization reaches a specific technological threshold. Nuclear weapons, radio telescopes, spaceflight, some marker that indicates we're becoming relevant on a galactic scale. 3i Atlas could be waking up now because we've finally crossed that threshold, or because something we did recently triggered an automated response protocol built into hardware that's been drifting through space since before Earth had continents. These are unverified scenarios, thought experiments rather than scientific conclusions, but they're not baseless speculation. They're extrapolations from principles we understand, applied to questions we're only beginning to know how to ask. And 3i Atlas, whatever it turns out to be, has forced those questions into mainstream scientific discourse, because if these objects are artificial, if we're being catalogued by a network we didn't know existed, then everything changes. Our place in the cosmos, our understanding of intelligence and civilization, our assumptions about being alone or unique, all of it gets rewritten. And we have to confront the possibility that we've never been alone at all. We've just been too primitive to notice the watchers until now. But here's what should really keep you up at night. While astronomers debate the nature of 3i Atlas, a parallel revolution is happening in how we observe the sky. And the timing is either an enormous coincidence or evidence that we're entering a new phase in cosmic awareness. Artificial intelligence has arrived in astronomy, and it's changing everything about how we detect, catalogue and interpret objects moving through our solar system and beyond. The machines are learning to see patterns we can't, finding signals in noise we dismiss, and in the process they're discovering things that make 3i Atlas look straightforward by comparison. The revolution started quietly, the way most paradigm shifts do. Astronomers have been using computer algorithms to analyze telescope data for decades. Nothing new there. But recent advances in machine learning have crossed a threshold where AI systems don't just process data faster than humans, they process it differently, applying pattern recognition techniques that can identify subtle correlations invisible to human observers, no matter how carefully they look. An AI trained on millions of stellar observations doesn't just categorize stars by brightness and color. It finds weird outliers, objects that don't fit any existing category, events that happen too quickly or too faintly for traditional surveys to catch. Microflares are a perfect example. These are tiny, brief brightenings in stars or other objects, lasting sometimes less than a second, releasing energy equivalent to a small nuclear bomb, but spread across electromagnetic wavelengths that make them nearly impossible to detect without specialized equipment and analysis. For years, we assumed microflares were rare because we rarely saw them. Turns out we just weren't looking properly. AI-powered telescopes now detect microflares constantly, thousands per night, and nobody's quite sure what they all mean. Some are probably natural stellar activity, others might be starquakes or magnetic reconnection events. But a few defy easy explanation, showing energy distributions or timing patterns that don't match any known astrophysical process. Microlensing events are even stranger. These occur when a massive object passes between Earth and a distant star, and the object's gravity bends the starlight in a way that briefly magnifies the background star's brightness. Microlensing has been used for years to detect exoplanets and dark matter candidates, but AI systems are finding microlensing events caused by much smaller objects, things too tiny to be planets, moving at velocities that don't fit normal solar system or galactic orbits. Some of these detections last milliseconds. Some show asymmetric brightness curves, suggesting non-spherical lensing objects, and a handful exhibit characteristics that researchers describe privately as troubling, though publicly they're just catalogued as anomalies pending further analysis. Transient objects are the real frontier. These are things that appear in telescope images for one frame and then vanish, present for hours or minutes before moving on or fading below detection limits. Before AI, most transients were missed entirely because nobody had time to examine every single image from every single telescope, looking for faint dots that might or might not be real. AI can examine millions of images in the time it takes a human to check one, and it's finding transients everywhere. Most are asteroids or satellites. Some are cosmic rays hitting the detector, but others have proper motion, moving across the sky in ways consistent with real objects at specific distances, and their velocities or trajectories occasionally raise eyebrows. The new survey arrays coming online make this even more intense. The Vera Rubin Observatory in Chile will photograph the entire visible sky every few nights, generating petabytes of data that no human team could possibly analyze manually. The Euclid Space Telescope is mapping the geometry of the universe while simultaneously cataloguing everything that moves or changes. The Nancy Grace Roman Space Telescope, set to launch soon, will conduct microlensing surveys orders of magnitude more sensitive than anything previously attempted. Each of these instruments feeds data into AI systems designed to find anomalies, and they're succeeding beyond anyone's expectations. But here's the uncomfortable part. Some research teams have detected things they're not publishing, not because of conspiracy or cover-up, but because the detections are too anomalous to present without more data. And getting more data is difficult when you're tracking objects that appear briefly and then vanish. Academic careers are ruined by publishing extraordinary claims that can't be replicated. So when an AI flags something genuinely weird, a microflare from an empty patch of sky, or a transient moving at 2% the speed of light, or a lensing event that suggests an object with impossible mass, the researchers sit on it. They wait for confirmation, they run more checks, and meanwhile the anomaly sits in a database somewhere. Flagged but not announced, unexplained but not forgotten. There are whispers in certain astronomy circles about a class of detections informally called fast movers, objects tracked by multiple telescopes showing velocities inconsistent with natural solar system objects but below escape velocity. Not fast enough to be interstellar, not slow enough to be captured, just weird intermediate speeds that require specific and unusual trajectories. Some people think these are classified satellites or debris from undisclosed military launches. Others aren't so sure, especially when the objects show brightness variations suggesting tumbling or unusual shapes. Then there's the reflectance curve problem. Most objects in space have predictable albedos. They reflect sunlight in ways consistent with rock or ice or metal. AI systems analyzing light curves from known asteroids sometimes find outliers, objects that reflect light with efficiency curves suggesting highly polished surfaces or geometries that don't occur naturally. These could be measurement errors. They could be strange mineral compositions, Or they could be something we haven't considered, materials or structures that don't fit our assumptions about what space debris should look like. The timing of all this matters. 3i Atlas arrives during the same period that our observational capabilities undergo exponential improvement. We're suddenly able to see things we couldn't see before, and what we're seeing is stranger than expected. Maybe that's coincidence. The universe is vast and weird, and better telescopes naturally find more weirdness. But there's another interpretation, one that keeps some astronomers up at night. Maybe we're not discovering new phenomena. Maybe we're finally noticing things that have always been there, objects and events that have been happening around us for years or centuries or longer, invisible until we built machines smart enough to spot them. If 3i Atlas represents intentional activity, if it's deploying probes around Jupiter while we watch, then the question becomes whether it's alone. Are there other objects we've missed? Are there networks already in place that our old telescopes couldn't detect, but our new AI-enhanced systems are starting to glimpse? Every anomalous detection, every unexplained transient, every microflare that doesn't quite make sense could be evidence of a presence we're only now learning to recognize. And here's the truly unsettling thought. While 3i Atlas approaches Jupiter, while AI systems scan the sky with unprecedented sensitivity, we're reaching a moment where both sides of the cosmic equation are changing simultaneously. They're arriving, or becoming visible, or activating, or whatever verb applies to interstellar probes beginning their missions, and we're learning to see, developing the technology and algorithms necessary to detect things that were previously invisible. Two curves intersecting, one inbound, one outward in capability, meeting at a point in time that feels less like coincidence and more like synchronization. Are we learning to see the universe more clearly just as something out there decides to take a closer look at us? Or have they been here all along, waiting patiently for us to develop eyes sophisticated enough to notice them? The answer might be encoded in the data our AI systems are collecting right now. Patterns hidden in millions of observations that we haven't yet learned to interpret. And when we finally decode those patterns, when we understand what the machines are seeing, we might discover that our solar system has never been as empty as we believed. We might find that we're surrounded by architecture we mistook for nature, probes we catalogued as comets, signals we dismissed as noise, and 3i Atlas, with its precision trajectory toward Jupiter's hill radius, might turn out to be not an isolated visitor, but the first one we noticed in a crowd we're only beginning to see. Now let's talk about something that's been bothering researchers since they first calculated 3i Atlas's trajectory, the antitail. This is one of those details that sounds technical and boring until you understand what it actually means. And what it means is deeply, profoundly strange. Most comets have tails that point away from the sun, that's basic physics. Solar radiation and solar wind push dust and gas outward, creating the characteristic tail that makes comets look like they're flying through space with streaming hair. Sometimes comets develop what's called an anti-tail, a spike that appears to point toward the sun. But these are optical illusions, perspective effects caused by viewing geometry. You're seeing part of the regular tail that happens to lie along your line of sight, making it look like it's pointing the wrong direction. Except 3i Atlas's anti-tail isn't an optical illusion. It's real, it's persistent, and it shouldn't exist. The anti-tail extends roughly 1 million kilometers sunward from the nucleus. That's not a typo. 1 million kilometers pointing directly toward the sun, against the solar wind, against radiation pressure, against every force that should be pushing material away from the star. To put that in perspective, that's more than twice the distance from Earth to the Moon. That's a structure stretching across space in a direction that physics says it shouldn't be able to maintain. Multiple observatories have confirmed this. It's not a measurement error. It's not a trick of the light. There is material streaming from 3i Atlas toward the sun, and nobody can adequately explain how it's happening. The conventional explanation invokes exotic outgassing dynamics. Maybe the nucleus is ejecting material at extremely high velocities, fast enough to overcome solar wind and radiation pressure, at least temporarily. Maybe there's some kind of magnetic field interaction we don't understand. Maybe the composition is so unusual that standard models of comet behavior don't apply. These are all possibilities, but none of them fit the observations particularly well. High-velocity ejection would require enormous energy, more than you'd expect from passive solar heating. You'd need active processes, maybe subsurface explosions as volatile pockets suddenly decompress, to generate the speeds necessary to push material sunward against the solar wind. And even then, you'd expect the antitail to be transient, appearing during outburst events and then fading. Instead, it's been consistently visible for months, suggesting continuous or frequently repeated ejection at improbable velocities. Magnetic field interactions are even more problematic. Comets don't generate their own magnetic fields strong enough to affect ionized gas trajectories on these scales. The solar magnetic field exists, sure, but it's oriented to channel material away from the sun, not toward it. You'd need a local magnetic anomaly, something about 3I Atlas itself, that creates field geometries capable of steering ionized material against the dominant flow. That's theoretically possible if the nucleus contains magnetic minerals, or if there's some kind of charge separation happening in the coma, but we've never seen anything like that in any other comet. It would be genuinely unprecedented. So here's the uncomfortable alternative. What if the anti-tail isn't outgassing at all? What if it's exhaust? Think about what a propulsion system does. It ejects mass in one direction to generate thrust in the opposite direction. If you want to slow down, if you want to shed velocity as you fall toward the inner solar system, you thrust in the direction opposite to your motion. For an object on an inbound trajectory, opposite to motion generally means sunward because you're moving from the outer solar system toward the sun. A continuous sunward pointing exhaust would indicate a braking maneuver, an attempt to reduce velocity to achieve a specific trajectory or prepare for orbital insertion. That explanation fits the observations perfectly. It accounts for the persistence, the energy, the directionality. It explains why the anti-tail has remained stable across months of observation. It's not chaotic outgassing. It's controlled thrust, aimed, calculated, executed with precision. If that's what we're seeing, if 3I Atlas has been running its engines this entire time we've been watching, then the implications are staggering. It means we've been observing active propulsion from an interstellar vehicle. It means the approach to Jupiter's hill radius isn't coincidence. It's navigation. And it means that whatever 3I Atlas is, it's been making adjustments all along, fine-tuning its path toward the target while we catalogued it as a comet and debated whether natural processes could explain the anomalies. But here's what makes this even more disturbing. The anti-tail appeared after perihelion. Before the Sun encounter, there were hints of a symmetric coma structure, but nothing like the pronounced sunward spike that emerged afterward. It's as if 3I Atlas needed to get close to the Sun first, needed that solar energy for something, and then afterward activated systems that created the anti-tail. Charging batteries, powering up equipment, executing a major course correction once sufficient energy was available. These are wild speculations, but they fit a pattern that's becoming harder to ignore. Every anomaly, every unexplained observation, every deviation from expected cometary behavior points in the same direction, toward intent, toward design, toward something that knows what it's doing and has specific goals it's working to achieve. The scientific establishment resists this interpretation, and for good reasons. The burden of proof for claiming artificial origin is enormous. You can't just point at anomalies and say aliens. You need to rule out every natural explanation first, and that's a high bar to clear. But at what point do the anomalies pile up enough that the natural explanations become more far-fetched than the artificial ones? At what point does Occam's razor flip, and the simplest explanation becomes it's a probe, rather than it's a comet with 6 different unprecedented properties that all happen to mimic what a probe would do? We might be approaching that point. The trajectory precision, the solar conjunction acceleration, the Earth flyby indifference, the hill radius targeting, the anti-tail, the coma stability. Each one individually could be explained naturally with enough assumptions, but together they paint a picture that's hard to reconcile with random chance and unusual ice distribution. And the picture they paint is of something that arrived from another star system, with a mission. Something that's been executing that mission with methodical precision since entering our solar system. Something that's almost at its destination now, approaching the gravitational boundary, where it can deploy whatever payload it's been carrying across the light years. We're watching it happen in real time. The question is whether we'll recognize deployment when we see it, or whether we'll catalogue it as natural fragmentation and miss the significance entirely until it's too late to do anything but realize what we witnessed. That's where we stand. Weeks away from the Jupiter encounter, days away from 3I Atlas crossing into the hill radius, hours away from the moment when theories get tested against reality and speculation gets replaced by observation. Every telescope that can reach Jupiter will be watching. Every instrument capable of detecting fragmentation or trajectory, changes or emissions will be recording. We're going to get answers, or at least we're going to get more data, and that data will either put the artificial probe hypothesis to rest once and for all, or it will confirm what a growing number of researchers are starting to believe, that we're not alone, that we've been visited, that something from beyond our star-built machines designed to explore the galaxy, and one of those machines is here right now, setting up shop in our cosmic neighbourhood whether we like it or not. The countdown has begun, the approach continues, and whatever happens next at Jupiter will be remembered as either the moment we learned comets can be weirder than we thought, or the moment everything changed. But before that moment arrives, before we see what 3i Atlas does when it reaches its destination, there's one more aspect of this mystery we need to examine: the question of why now. Why is this happening during our lifetimes? Why are we the generation that gets to witness first contact if that's what this is? The timing question haunts every conversation about 3i Atlas among researchers who take the artificial hypothesis seriously. Because if interstellar probes are common, if the galaxy has been seeded with Sentinel networks over millions of years, then statistically, the odds that we'd be alive during the exact period when one arrives and deploys are vanishingly small, unless the arrival isn't random. Unless there's a reason it's happening now, one possibility is that we triggered it. That hypothesis suggests probe networks have been in our solar system for a long time, dormant, waiting for specific conditions before activating. What conditions? Technological development is the obvious candidate. Radio transmissions that indicate electromagnetic sophistication. Nuclear detonations that demonstrate energy manipulation at atomic scales. Spacecraft leaving Earth's atmosphere, proving we've achieved spaceflight. Each of these milestones could serve as a trigger, an automated wake-up signal for dormant systems that have been quietly orbiting in the outer solar system for centuries or millennia. From this perspective, 3i Atlas isn't arriving, it's responding. Something we did in the past few decades flipped a switch in hardware that was already here, causing it to move from passive observation to active deployment. The timing makes sense under this model. We've been broadcasting radio for about a century. We detonated the first atomic bomb in 1945. We reached orbit in 1957. We landed on the moon in 1969. Any of these events could have served as the trigger that told a waiting probe network, this civilization has reached technological adolescence, time to deploy closer observation assets. The alternative timing explanation is more disturbing. Maybe the arrival is random, but our ability to notice is not. Think about it. 20 years ago, we wouldn't have detected 3i Atlas at all. Our surveys weren't sensitive enough. Our tracking wasn't comprehensive enough. Even 10 years ago, we might have caught it, but dismissed the trajectory calculations as uncertain, or archived it as a long-period comet without realizing its interstellar origin. The fact that we detected it, tracked it, and recognized its anomalies says more about how much our observational capabilities have improved than about the object itself, which raises a terrifying possibility. What if interstellar objects like 3i Atlas pass through regularly, every few decades or every century, and we're only now reaching the technological threshold where we can see them? What if our solar system has been hosting a parade of visitors for thousands of years, and we're just now developing the eyes to notice? That would mean we've been under observation far longer than we realized. That would mean the watchers have been cataloguing us through our entire technological development, through world wars and space programs and the dawn of the internet, recording everything while we remained oblivious. There's yet another timing explanation that's even more unsettling: convergence. The idea that there's a natural correlation between a civilization developing the technology to detect interstellar probes and those probes becoming more active or visible. Not because the probes are responding to our development, but because both events are tied to the same underlying factor: electromagnetic activity. Think about it. A civilization that develops radio astronomy, that builds sensitive receivers capable of detecting faint signals from distant sources, is simultaneously broadcasting its own signals into space with increasing intensity. The same telescopes that let us detect 3i Atlas also make us visible to anyone or anything listening. Maybe probe networks don't activate based on simple binary triggers. Maybe they're continuously monitoring electromagnetic output from target systems, and when that output crosses certain thresholds, indicating sophisticated signal processing capability, the probes adjust their behavior accordingly. Not hiding anymore because there's no point. The civilization can see them now. Might as well move into position for closer observation since stealth is no longer viable. Under this model, we're experiencing first contact not because they decided to reveal themselves, but because we developed the ability to see them, and they're adapting to that new reality by repositioning assets to locations where they can continue observing us effectively, despite our improved detection capabilities. Jupiter's Hill radius makes perfect sense in this context. Far enough out that we can't easily interfere, close enough that Earth remains well within observation range, and positioned in a radiation environment that still provides significant protection against detailed scanning from our primitive instruments. There's also the possibility that none of these timing explanations are correct. Maybe it really is just coincidence. The galaxy is old and vast. Interstellar probes have been wandering for millions of years. Eventually one of them passes through our system during the brief window when we're technologically capable of noticing. Pure chance. Bad luck or good luck, depending on your perspective. But astronomers are trained to be suspicious of coincidences, especially when the coincidence involves multiple, low-probability events occurring simultaneously. It feels like there should be a connection between our technological development and the arrival of 3I Atlas. The alternative, that it just happened to show up during the century when we could first detect it, feels too convenient. Then there are the researchers who think the timing question is a distraction. They argue that if 3I Atlas is artificial, if it represents a probe from an advanced civilization, then the concept of arrival might not mean what we think it means. Maybe it didn't travel here recently. Maybe it's been in the solar system for a long time, possibly since before humans existed, following a complex trajectory that loops through the system over and over, periodically approaching planets of interest. What we're seeing might not be first arrival, but rather the latest in a series of approaches that have been happening for millennia. This hypothesis fits with certain observations about 3I Atlas's velocity and trajectory. The object isn't moving at the kind of relativistic speeds you'd expect from something that just finished a million-year journey through interstellar space. It's moving fast by human standards, but slowly by interstellar standards, almost as if it's been gravitationally captured and has been orbiting within the solar system for a while, periodically diving inward for closer looks at the inner planets before swinging back out to the periphery. If that's true, then this isn't first contact. This is just the first time we've been sophisticated enough to notice one of the regular visits. The implications of each timing scenario are profoundly different. If we triggered the deployment, that suggests a level of automation and patience in the probe network that's both impressive and unsettling. They've been waiting potentially for thousands of years, quietly observing, until we crossed the threshold that activated closer examination. If the timing is coincidental, then we got extremely lucky or unlucky, witnessing something that happens rarely and unpredictably. If we're seeing them because we've finally developed the capability, then the galaxy might be full of these things, and we're just now joining the club of civilizations that can detect them. And if they've been here all along, if 3I Atlas is on a routine orbit that brings it through regularly, then the question becomes, why didn't we notice before? Were previous passages during times when we weren't looking carefully enough? Or has something changed about 3I Atlas itself, some aspect of its operation that made it more visible this time compared to previous approaches? Whichever explanation is correct, the timing question adds another layer of strangeness to a situation that's already overflowing with anomalies. Now let's talk about what happens if we're right. If 3I Atlas is artificial, if it deploys a network of probes around Jupiter, if we confirm beyond reasonable doubt that we're being observed by technology from another star, what happens next? That question has been keeping policymakers up at night ever since the trajectory calculations started suggesting something unusual was happening. Because there are no protocols for this, no agreed-upon international framework for how to respond, no chain of command for deciding who speaks for humanity if speaking becomes necessary. The scientific community has some guidelines. The SETI protocols developed over decades of thinking about how to handle detection of extraterrestrial intelligence provide a roadmap for verification and announcement. First, confirm the detection independently. Multiple teams, multiple instruments, multiple methodologies to eliminate any possibility of error or misinterpretation. Second, inform relevant authorities quietly before going public. Give governments time to prepare for the societal impact. Third, make a coordinated announcement through established channels, presenting the evidence clearly and avoiding sensationalism. And fourth, continue observation and analysis while remaining open to contact if contact is offered. These protocols were designed for Radio SETI, for detecting signals from distant civilizations. 3i Atlas is different. It's not distant. It's here, in our solar system, close enough that we can watch it in real time. It's not broadcasting, it's moving, and if it's artificial, it's not trying to talk to us, it's positioning itself to watch us. The SETI protocols don't really address this scenario. They were built around the assumption that first contact would be unambiguous communication from a civilization light years away, not ambiguous observation from hardware in our cosmic backyard that might or might not even acknowledge our existence. So what actually happens if deployment is confirmed? First, there would be an emergency meeting of the UN Committee on the Peaceful Uses of Outer Space. This is the international body nominally responsible for coordinating humanity's activities in space. They'd convene representatives from major space agencies, NASA, ESA, Roscosmos, CNSA, ISRO, and relevant scientific organizations. The discussion would be chaotic. Some nations would push for immediate transparency, arguing that the public has a right to know. Others would advocate for controlled release of information to prevent panic. And a few would probably try to keep it secret entirely, at least until they figure out whether there's any way to exploit the situation for national advantage. The scientific community would split into two camps. One camp would argue that observation should continue without any attempt at interaction. Don't do anything that might be interpreted as aggressive. Don't signal. Don't approach. Just watch and learn while maintaining as low a profile as possible. The reasoning is simple. We don't know what we're dealing with. We don't know the capabilities or intentions of whatever built these probes. Doing something stupid could provoke a response we're not prepared for. Better to stay quiet and gather information. The other camp would argue that interaction is not only appropriate but necessary. If they're watching us, they already know we're here. Pretending we don't see them is pointless, and possibly insulting. We should make an attempt at communication, even if we don't expect a response. Shine lasers at the probes, broadcast messages on multiple frequencies, launch a mission to approach one of the deployed units if possible. Demonstrate that we're intelligent, curious, and willing to engage peacefully. The reasoning here is that passive observation is undignified. We're not lab rats to be studied without our knowledge or consent. If contact is happening, we should be active participants, not passive subjects. Both positions have merit. Both have risks, and there's no obvious way to reconcile them, which is why the debates would be fierce and probably unproductive. Meanwhile, media would be in a frenzy. Even if governments tried to manage the information release, leaks would be inevitable. Too many people involved, too many institutions with access to the data. Within days, possibly hours, the story would be global news. And once it's out there, controlling the narrative becomes impossible. You'd have talking heads on every network offering opinions, conspiracy theorists spinning wild theories about government cover-ups and alien agendas, religious leaders interpreting the revelation through theological frameworks, scientists trying desperately to communicate nuance and uncertainty while being pushed for definitive statements they can't make. The psychological impact on the general public is difficult to predict. Some studies suggest that confirmation of extraterrestrial intelligence would be less traumatic than expected. Most people already believe it's likely that aliens exist somewhere in the universe. Finding out that belief is correct might not be that shocking. But there's a difference between abstract belief and concrete confirmation. And there's an even bigger difference between knowing aliens exist somewhere out there and knowing they're here, watching us, setting up infrastructure in our solar system. That crosses a psychological boundary that might trigger reactions we can't anticipate. You'd see a surge in apocalyptic thinking. If they're here, some people will assume invasion is imminent. Prepare for the worst. Stock up on supplies. Some governments might use the situation to justify increased military spending or emergency powers. The logic would be that if we're being observed, we need to be ready to defend ourselves if observation turns to action. This despite the fact that any civilization capable of sending probes across interstellar distances almost certainly has technology so far beyond ours that military preparation is meaningless. But that logic won't stop the political exploitation of fear. Conversely, you'd also see a surge in utopian thinking. Contact would be interpreted as validation that we're not alone, that intelligence and consciousness are universal, that humanity has cosmic company. This could inspire movements toward global unity, efforts to present a better face to the watching eyes, clean up the planet, end conflicts, demonstrate that we're worthy of acknowledgement. These impulses are noble, but also naive. The watchers, if that's what they are, have probably been observing for long enough to know exactly what kind of civilization we are. Sudden attempts to improve our behaviour wouldn't fool anyone. Then there's the religious response, which would vary enormously, depending on theology and cultural context. Some faiths might integrate the revelation smoothly, interpreting extraterrestrial intelligence as part of divine creation. Others might face existential crises, struggling to reconcile sacred texts with the reality of advanced beings from other worlds, and a few might reject the evidence entirely, declaring it a hoax or demonic deception. The diversity of responses would create new fault lines in societies already struggling with polarization and information warfare. Economically, confirmation of artificial probes would probably trigger market instability, at least in the short term. Not because of any direct threat, but because uncertainty is bad for markets. Investors don't know how to price the risk of having alien surveillance in the solar system. Is this good for humanity long term? Bad? Neutral? Without clear answers, capital gets cautious. You'd see volatility in tech stocks as speculation grows about what we as a society might learn from observing the probes. You'd see shifts in space industry investments as governments and private companies reassess priorities in light of the new reality. And you'd probably see a boom in space-related industries as everyone tries to position themselves for whatever comes next. Scientifically, the confirmation would be the most significant event in history. It would validate astrobiology as a discipline. It would prove that the galaxy produces technological civilizations. It would provide our first data point for the Drake equation beyond our own existence. The implications for physics, engineering, sociology, philosophy, every field would be profound. Graduate students would be scrambling to reorient their dissertations toward questions suddenly relevant. Funding agencies would redirect resources toward probe-related research, and institutions would compete fiercely to lead the new era of contact science. But all of that assumes we get confirmation, and that's not certain. The deployment, if it happens, might be subtle enough that debate continues. Objects separating from 3i Atlas and moving toward Lagrange points could still be explained as natural fragmentation, if you're determined to maintain that interpretation. Lack of obvious communication, or dramatic activity, could be cited as evidence against artificial origin. The conservative interpretation would be that we saw a weird comet do weird things. Interesting but ultimately explicable. Nothing that proves intelligence beyond Earth. And that interpretation would have institutional weight behind it. Because institutions are conservative by nature, they don't like paradigm shifts. So even if deployment happens exactly as predicted by the artificial hypothesis, even if probes position themselves at L1 and L2 and settle into orbits that make surveillance sense, there would still be scientists arguing it's all natural, coincidence, unusual but not unprecedented, just ice and rock behaving strangely under conditions we don't fully understand, and the debate would continue, unresolved, contentious, splitting the community into factions that view the same data through incompatible frameworks. That might be the most frustrating outcome. Not definitive confirmation, not clear refutation, just more ambiguity, more uncertainty, more arguments that go nowhere, because the evidence permits multiple interpretations. But here's what I think would actually happen if we got clear, unambiguous confirmation that 3i Atlas is artificial. I think there would be an initial period of shock and denial, a week, maybe 2, where the information spreads but hasn't fully sunk in. People would go through their daily routines in a kind of daze, intellectually aware that everything just changed but not emotionally processing it yet. Then would come the reckoning, the moment when the reality hits. We're not alone, we've been visited. Something from beyond our star is here, watching us, and we have no idea what comes next. That moment would be different for everyone. For some it would be terrifying, for others exhilarating, for many probably both simultaneously, but it would mark a before and after in human consciousness. Before we knew and after we knew, and everything that happened subsequently would be coloured by that knowledge. Every decision about space exploration, every discussion about humanity's future, every debate about what we should be doing with our civilization. All of it would happen in the context of knowing we're being observed by something that crossed the stars to get here. The long-term effects are even harder to predict. Does confirmation of surveillance lead to increased unity or increased division? Does it inspire us to reach for the stars ourselves, or make us withdraw inward in fear? Does it change how we think about our place in the universe, or just become another background fact we learn to live with, like knowing the sun will eventually die or that the universe is expanding? These questions won't be answered immediately. They'll unfold over decades as we adapt to the new reality and figure out what it means for how we live and what we aspire to become. Now let's talk about the observation plan for the Jupiter encounter, because this is where rubber meets road, where speculation gets tested against reality, where we find out if months of debate and analysis have been pointing towards something real or if we've been chasing shadows. The campaign is unprecedented in scope. Every major telescope that can reach Jupiter will be pointed at 3i Atlas as it crosses into the Hill radius. Hubble Space Telescope has dedicated time, James Webb has scheduled observations. Ground-based facilities from Chile to Hawaii to the Canary Islands are coordinating to provide continuous coverage. The goal is to miss nothing, to capture every moment of the approach and whatever happens afterward with as much detail and redundancy as possible. What specifically are they looking for? First, trajectory changes. As 3i Atlas enters the Hill radius, gravitational forces become complex. Jupiter's pull dominates, but the Sun is still significant. Any deviation from purely gravitational motion would be detectable if instruments are watching closely. If the object makes course corrections, if it adjusts velocity in ways that can't be explained by gravity and outgassing, that's a smoking gun. Second, fragmentation. Natural comets sometimes break apart when tidal forces exceed the structural strength holding them together. But fragmentation that results in pieces moving to specific locations rather than dispersing randomly would be suspicious, especially if those locations happen to be gravitationally stable points like Lagrange positions. Third, emission changes. Spectroscopic monitoring will track the coma composition continuously. If the chemical makeup shifts in ways that suggest activation of different systems, if new emission lines appear that weren't there before, if the intensity or distribution changes suddenly, that tells you something happened to the object's activity state. Fourth, rotation and tumbling. Natural comets have chaotic rotation patterns that change over time due to outgassing torques. Artificial objects might maintain stable attitudes or change orientation in controlled ways. High-speed photometry will measure brightness variations at sub-second timescales, looking for periodicities or anomalies that don't fit tumbling models. Fifth, electromagnetic emissions. Radio telescopes will scan for any signals coming from 3i Atlas or from the Jupiter environment. They're not expecting messages. They're looking for leaked electronics, the kind of radio noise that modern electronics produce as a side effect of operation. Even shielded systems emit some stray radiation. If there's active technology aboard, there should be some signature in the electromagnetic spectrum. Sixth, infrared anomalies. JWST's infrared sensitivity can detect temperature variations that might indicate internal heat sources. Natural comets should have surface temperatures determined by solar heating. Artificial probes might have warm spots where energy is being generated or dissipated. Seventh, and this is subtle, differential tracking. By measuring the object's position extremely precisely over time, you can detect forces that aren't gravitational. If 3i Atlas experiences acceleration that can't be explained by Jupiter's gravity, or solar radiation pressure or outgassing, that's evidence of propulsion. The measurements required are at the edge of what's possible, but modern astrometry can detect position shifts of microarc seconds. Over weeks of observation, that precision adds up to meaningful constraints on non-gravitational forces. The observation campaign has contingencies. If initial data suggests something unusual is happening, secondary protocols kick in. Additional telescope time gets allocated. Space-based assets get retasked. Rapid response teams are standing by to analyze incoming data and adjust observation strategies in real time. There's particular focus on the period immediately after Hill radius crossing. That's when deployment would most likely occur if it's going to happen. The object has reached its destination. It's in the gravitationally stable zone. If it's a carrier, this is when it would release payload, so the hours surrounding that crossing will have maximum coverage. Multiple telescopes watching simultaneously from different angles to triangulate any events that occur. spectrographs running continuously to catch compositional changes, photometry at high cadence to detect brief events that might be missed by slower observations. The data volume will be enormous, terabytes flowing in from multiple sources, all time-stamped and calibrated, ready for analysis. The analysis itself will happen in stages. First pass is automated, algorithms scanning for obvious anomalies, objects separating, trajectory deviations, unexpected emissions. Anything flagged by the automated systems gets immediate human review. Second pass is detailed, experts examining the data carefully, comparing observations across different instruments, building models to explain what's being seen. Third pass is verification, independent teams working with the same data to see if they reach the same conclusions. Only after verification does anything get announced publicly. The timeline from observation to announcement could be days or weeks depending on how clear the data is. If something unambiguous happens, if 3i Atlas obviously fragments and the pieces move to stable orbits, the announcement might come quickly. If the results are subtle or ambiguous, if different teams reach different conclusions, the process takes longer. Science doesn't move at the speed of Twitter, no matter how much public pressure there is for instant answers. There's also a political dimension. If the data suggests artificial origin, governments will want to be consulted before public announcement. That could add days or weeks to the timeline as various parties argue about messaging and coordination. The scientific community generally resists political interference in announcements, but when the implications are this significant, pragmatism might win out. Better to have governments on board than to trigger panic by announcing prematurely. Meanwhile, amateur astronomers will be watching too. You can't hide Jupiter. Thousands of capable amateur telescopes around the world will be pointed at the same region of sky, collecting their own data, posting images and videos online in real time. This creates both opportunities and challenges. Opportunities because distributed observation provides redundancy and different perspectives. Challenges because premature or incorrect interpretations might spread before the professionals can properly analyze the data. Social media will light up with speculation. Every image will be scrutinized for evidence of deployment. Every anomaly will be amplified and debated. The professional community will try to stay focused and rigorous, while the public conversation spirals in every direction. It's going to be a mess. An exciting, terrifying, historically significant mess. But it's necessary. This is too important to handle behind closed doors. The observations need to be as open and transparent as possible. The data needs to be available for independent analysis. The conclusions need to be replicable and verified by multiple teams. That's how science builds confidence in results, especially results as extraordinary as confirming alien technology in our solar system. So what's my prediction? What do I actually think is going to happen when 3i Atlas reaches Jupiter? Honestly, I don't know. The evidence is tantalizing but not definitive. The anomalies are real but potentially explicable. The trajectory precision is remarkable but maybe not impossible for natural processes. I lean toward thinking there's something genuinely strange going on here. Whether that strangeness is alien technology or just exotic natural phenomena we haven't encountered before, I can't say. But I know we're about to find out. The encounter is imminent, the observations are planned, the instruments are ready. In a matter of weeks, maybe days, we're going to have data that will settle some questions and probably raise a dozen new ones. What I can say with confidence is that 3i Atlas has already changed astronomy. It's forced us to take interstellar objects seriously. It's pushed the artificial probe hypothesis from fringe speculation to legitimate scientific discourse. It's revealed how much we still don't understand about comets and how they behave, and it's reminded us that the universe is full of surprises, that our models and expectations are always provisional, subject to revision when nature shows us something we didn't anticipate. That's the heart of scientific thinking. Remain open to evidence even when it challenges comfortable assumptions. If 3i Atlas turns out to be a weird comet, that's fascinating and valuable. We'll learn about ice compositions and sublimation dynamics, and how objects from other stellar systems might differ from our own. If it turns out to be artificial, that's transformative. We'll have confirmed we're not alone and opened an entirely new chapter in human history. Either way we win. Either way we learn. And isn't that the point? Not to prove a pet theory correct, but to find out what's actually true regardless of whether it fits expectations. The universe doesn't care about our preferences. It is what it is, Our job is to observe it honestly and follow the evidence wherever it leads. So here we are, at the threshold, waiting for data that might answer the oldest question humanity has ever asked. Are we alone? The answer might be hiding in the trajectory of an interstellar comet, or it might not. But we're finally in a position to check. We have the instruments, we have the methodology, we have the will to ask the question seriously and accept whatever answer emerges. That's remarkable in itself, that we've reached a point technologically and intellectually where we can investigate these questions rigorously, rather than just speculating about them philosophically. A century ago, the idea of detecting interstellar objects was science fiction. 50 years ago, we were still debating whether planets existed around other stars. 20 years ago, we'd never confirmed a single interstellar visitor, and now we're tracking our third one, debating whether it's artificial, planning observation campaigns to catch deployment events. The pace of progress is staggering, and it's accelerating. The Vera Rubin Observatory comes online soon. The Nancy Grace Roman Space Telescope launches in a few years. New instruments and surveys that will find dozens of interstellar objects annually instead of one every few years. Each detection is another chance to test hypotheses, another data point in understanding what's normal and what's anomalous. If 3I Atlas is the first confirmed artificial probe, it won't be the last. Once we know what to look for, once we understand the signatures that distinguish natural from artificial, we'll start finding more. Building a catalogue, learning patterns, maybe discovering that Sentinel networks are common, that every star system has them, that we're joining a galactic community of observed civilizations whether we knew it or not. Or maybe we'll confirm that 3I Atlas was just a weird comet, and interstellar probes remain hypothetical. That would be disappointing in some ways, but also reassuring. It would mean the galaxy is less crowded than some scenarios suggest, that we have more time to develop and mature before encountering others. Either outcome teaches us something profound about cosmic context and where we fit. Before we close, I want to come back to the question that started this whole journey. What keeps astronomers up at night? It's not the big obvious threats. It's the subtle anomalies, the precision where there shouldn't be any, the patterns that don't quite fit, the evidence that suggests something significant is happening but stops just short of proof. That's what 3I Atlas represents, a collection of anomalies that individually might be dismissible, but collectively form a pattern that demands explanation. The Hill radius targeting, the solar conjunction acceleration, the Earth flyby indifference, the anti-tail, the trajectory stability. Every single one could be coincidence. Every single one could be natural process we don't fully understand. But together they suggest intentionality. Together they look like a mission being executed. And if that's what we're seeing, if 3I Atlas really is artificial, then the implications ripple outward in ways we're only beginning to grasp. It means the galaxy is populated. It means intelligence has arisen elsewhere and developed technology capable of crossing the stars. It means we're being studied, catalogued, observed by entities whose capabilities exceed ours by unknown margins. It means Earth's development, our entire history of civilization, might have been watched and recorded by silent witnesses we never noticed until now. It means contact has already happened, just not in the form we imagined. No radio messages, no dramatic landings, just patient observation from strategic positions, networks of probes quietly monitoring while civilizations rise and fall beneath their gaze. It means we need to rethink assumptions about our cosmic significance and timeline for contact. Maybe contact doesn't happen when civilizations reach out to each other. Maybe it happens when developing civilizations finally become sophisticated enough to notice the infrastructure that's been around them all, along. Like a child suddenly realizing adults have been in the room the entire time, watching, waiting to see if the child notices. That's a humbling and unsettling realization. It changes the psychology of cosmic solitude. We thought we were alone, calling into the void, hoping for response. But maybe we were never alone. Maybe the void has been full of watchers all along, and we're just now developing the eyes to see them. Just now reaching the maturity to recognize we're not the only players in a game that's been running for billions of years across the entire galaxy. That's heavy. That's world-changing if true. And that's why the Jupiter encounter matters so much. Because it might be the moment when suspicion becomes confirmation, when anomalies crystallize into evidence, when we stop wondering if we're being watched and start adapting to the knowledge that we are. The countdown continues. 3I Atlas moves inexorably toward its destination, Instruments are ready, observers are watching. And soon, very soon, we'll have our answer. Or at least the beginning of an answer, because in science, answers always lead to new questions. The unknown doesn't disappear, it just recedes, revealing new layers of mystery beneath. But that's okay. That's how it should be. We're not looking for final answers, we're looking for next questions, better questions. Questions informed by observation and evidence rather than speculation and assumption. And 3i Atlas, whatever it turns out to be, has given us better questions, has forced us to think more carefully about what's possible, what's likely, what's detectable, has pushed our observational capabilities and theoretical models to new limits, has reminded us that the universe is vast and strange and full of phenomena we don't understand yet. That's the gift. Not certainty, but curiosity. Not answers, but the motivation to keep looking, keep asking, keep probing the boundaries of knowledge until we understand our cosmic context more fully. So thank you, 3i Atlas, for being weird, for challenging assumptions, for making us question whether we're alone, for giving us something to debate and observe and puzzle over, and for reminding us that the most exciting moments in science come when nature refuses to fit in our boxes and forces us to build bigger boxes or abandon boxes altogether. The universe is speaking, through trajectory precision and anti-tails and hill radius intercepts, through every anomaly and every confirmed measurement. It's telling us something. We just need to listen carefully enough to hear what it's actually saying, rather than what we want it to say. The story continues, the approach continues, and whatever happens next, we'll be watching. Because that's what we do. We're the species that looks up and asks why, the species that builds telescopes to see further and theories to understand better, the species that can't leave mysteries alone, that has to investigate, has to know, to push the boundaries of understanding even when the answers might be uncomfortable. That drive, that curiosity, that refusal to accept ignorance when observation is possible, that's what makes us human. And 3i Atlas is testing that humanity in ways we never expected. Are we ready to accept evidence that challenges everything we thought we knew? Are we mature enough to handle confirmation that we're not alone? Are we wise enough to interpret observations correctly rather than seeing what we want to see? These questions matter as much as the technical questions about trajectories and propulsion. Because how we respond to 3i Atlas, how we process the data and reach conclusions and communicate findings that reveals who we are as a civilization at this moment in our development. And maybe that's part of the test. Maybe the watchers, if they exist, are observing not just our technology, but our methodology, not just our capabilities, but our character, how we handle uncertainty, how we debate evidence, how we balance skepticism with openness. Those traits matter for any civilization aspiring to join the cosmic community, if such a community exists. So let's do this right. Let's observe carefully. Let's analyze honestly. Let's debate vigorously but respectfully. Let's follow the evidence wherever it leads, whether that's toward natural explanations or artificial ones. Let's be worthy of the opportunity we've been given to witness whatever 3i Atlas represents. And let's remember that the universe is watching us watch it. Through our telescopes and instruments and analytical frameworks, we're revealing ourselves as much as we're revealing the cosmos. Make it count. Before we go, I need to know something. Where are you watching this from right now? Drop your location and what time it is where you are in the comments below. Because here's what's fascinating. While you've been watching this, 3i Atlas has travelled thousands more kilometres toward Jupiter. Someone in Tokyo is experiencing a different moment of its journey than someone in New York or London or Sydney. We're all tracking the same cosmic visitor, but from different perspectives, different times, different contexts. Hit subscribe and turn on notifications because the Jupiter encounter is happening soon. When 3i Atlas crosses into the hill radius, when deployment might occur or fragmentation might be observed or whatever happens actually happens, you're going to want to be among the first to know. Are we about to confirm the existence of alien technology in our solar system? Are we about to witness deployment of a surveillance network that will watch humanity for centuries to come? Or are we about to learn that comets can be weirder than we ever imagined? Drop your location and time below. Let's see how global this moment has become, and I'll see you in the next one when we break down what actually happened at Jupiter. History is being made, folks, and you're here for it.